Hello and welcome to Lapping Analytics, this time for a video on serial correlation in time series. My name is Jimmy Lapping, I'm a psychologist and statistician with already many years of experience in research, and time series data is one of my favorite topics. Time series phenomena are all around us. Think for example about the weather, the stock market, growth of people and animals, and what these different examples have in common with each other and distinguishes them from many other types of data is what is called serial correlation. Without going into too much technical detail, serial correlation means that previous observations to some extent define a range of reasonable predictions for next occasions. For example, although there is a certain volatility, the price of a stock on a given day is not just a purely random event. Given yesterday's close, some values are more likely to be observed today than others. And the same goes for many types of human behavior that can be monitored through time series data. In the remainder of this video, I will focus on an example of daily distances in kilometers walked by a person during a 28-day time window, the first half of which is before and the second half immediately following an informative intervention regarding potential health benefits of walking more. In this figure, you see the daily distances observed represented by red dots and a so-called autoregressive piecewise linear model to account for differences between the first and second half of the observed time interval. That is, this autoregressive model attempts to estimate the trend within each of the two phases and the difference in end point between both phases as well, while accounting for what is here the case a positive serial correlation. That is, days with longer distances walked are more likely to be followed by days with longer distances walked than by days with shorter distances walked. In a minute, I will provide some key statistics for this example participant as well as for two other example participants that display a positive serial correlation in their walking behavior. Now, some people have more of a rhythm in which days of longer distances walked are more likely to be followed by days with relatively shorter distances walked, and vice versa. And in this case, we speak of a negative serial correlation. In a minute, I will also provide some key statistics for this example participant as well as for two other example participants that display a negative serial correlation in their walking behavior. But let's start with the three examples of participants where there is positive serial correlation. Phi, which is an estimate of serial correlation, equals 0.49 in this first example. Is that a lot? Well, correlations can range between -1 and +1, and 0.49 is, in the context of human behavior, generally considered a fairly sizable or even strong positive correlation. In the table you see two models. On the left there is the ordinary least squares or OLS model. This is a classical linear regression model that most people with a bachelor's degree in any of the social or health sciences will have come across at some point or another. And that is widely used in research across the planet. This model is based on several assumptions, including that there is no serial correlation in the data. This is also referred to as the independence assumption because it basically states that all observations are independent and hence phi equals 0. On the right in the table, you see the autoregressive or AR1 model, which accounts for the fact that phi is not 0 and does so by assuming that the distance walked on a given day is to some extent a function of the distance walked the day before, hence AR1, with the 1 indicating 1 day back or the previous day. What you see here are point estimates B and standard errors SE, and as you can see, neither the point estimates nor the standard errors are the same between models. Without going into more mathematical detail on the meaning of the terms intercept, phase, count and phase by count, for which I can happily refer you to another video on my channel if that is of interest, the fact that these two models yield different point estimates and different standard errors is important. In addition, you see that all four standard errors are lower with the OLS model, which is the model that incorrectly assumes the absence of serial correlation. The standard errors returned by the AR1 model, which estimates phi to be 0.49 instead of 0, are about 1.5 times the standard errors of the OLS model. Is this difference in standard errors systematic, or is it just an artifact occurring for this specific participant? Well, let us have a look at another example participant. Again, we see serial correlation phi equaling 0.49, and again the standard errors returned by the AR1 model are about 1.5 times the standard errors of the OLS model. And if we have to deal with a participant where this positive serial correlation is even stronger, as is the case here, we see that the difference in standard errors between both models may well be a factor 2 or 3. In sum, in the presence of positive serial correlation, the OLS model, which incorrectly assumes zero serial correlation, tends to provide different point estimates than the AR1 model and systematically underestimates the standard errors. And how is the situation when we have to deal with negative serial correlation? Well, here a first example where phi is about minus 0.4, in other words, a fairly sizable negative serial correlation. And in this case, well, we see again different point estimates between models, but this time we see that the difference in standard errors is about a factor of 1.5 in the other direction. That is, larger standard errors with the OLS model. And when we deal with a case where the negative serial correlation is even stronger, we see that the difference in standard errors between models may again exceed a factor 2, though now again given negative serial correlation, clearly larger standard errors with the OLS model. And to give a third example, again with a phi coefficient in the negative 0.40s, OLS systematically overestimates standard errors. So in a nutshell, compared to the AR1 model, which often provides a reasonable starting point for this kind of data, the OLS model systematically underestimates standard errors in the case of positive serial correlation, but systematically overestimates standard errors in the presence of negative serial correlation. So again, the OLS model systematically underestimates standard errors in the case of positive serial correlation, but systematically overestimates standard errors in the presence of negative serial correlation. And if you are into machine learning and think, well, I don't have this problem. Well, as long as the model used is OLS, you assume zero serial correlation and will probably get incorrect point and interval estimates regardless of how the model is trained. And if training outcome is garbage, so will be the outcome of any next step using that model. Finally, note that the kind of piecewise linear AR model used in this video is by no means the only possible solution to serial correlation. Several alternatives exist, some of which I talk about in other videos on my channel, but I did not want to turn this short video into a 2-hour lecture on time series research. That said, I hope you found this short video useful. And if you like this content, you can find plenty more of it on my channel. And meanwhile, if you have any comments or suggestions, just leave a note below the video. And for now, thank you for watching, thank you for listening, and have a great day.